If in some cataclysm all of the scientific knowledge were to be destroyed, and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, which simply says that all things are made up of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart but repelling upon being squeezed into one another. In that one sentence, you will see there is an enormous amount of information about the world if just a little imagination and thinking are applied to illustrate the power of the atomic idea. Let us take an example. This is the picture of a water drop magnified a billion times, but idealized in several ways. In the first place, the particles are drawn in a simple manner with sharp edges, which is inaccurate. Secondly, for simplicity, they are sketched almost systematically in a two-dimensional arrangement. But of course, they are moving around in three dimensions. Notice that there are two kinds of circles to represent the atoms of oxygen, black, and hydrogen, white, and that each oxygen has two hydrogens tied to it. Each little group of an oxygen with its hydrogens is called a molecule. The picture is idealized further in that the real particles in nature are continually jiggling and bouncing, turning and twisting around one another. You will have to imagine this as a dynamic rather than a static picture. Now imagine a great drop of water with all its particles bouncing and turning and twisting. Now, the jiggling motion is what we represent as heat. When the jiggling increases, we has increased the temperature, or when we increase the temperature, we increase the motion. If we heat the water, the jiggling of particles increases and the volume between the atoms increases. And if the heating continues, there comes a time when the pull between the molecules is not enough to hold them together, and they do fly apart and become separated from one another. Of course, this is how we manufacture steam out of water, by increasing the temperature. The particles fly apart because of the increased motion. In figure 1.2, you will see a picture. We have a picture of steam. This picture of steam fails in one respect. At ordinary atmospheric pressure, there certainly would not be as many as 3 water molecules in this figure. Most squares this size would contain none, but we accidentally have 2.5 or 3 in the picture. Let us see what some of the properties of steam, vapor, or any other gas are. The molecules, being separated from one another, will bounce against the walls. Imagine a room with a number of tennis balls, 100 or so, bouncing around in perpetual motion. When they bombard the wall, they push the wall away. This means that the gas exerts a force which our coarse senses feel only as an average push. In order to confine a gas, we must apply a pressure. Figure 1.3 shows a standard vessel for holding gases, which is used in all textbooks, a cylinder with a piston in it. Now it makes no difference what the shapes of water molecules are, so for simplicity we shall draw them as tennis balls or little dots. So many of them are hitting the top piston all the time that to keep it from being patiently knocked out of the tank by this continuous banging, we shall have to hold the piston down by a certain force, which we call the pressure. Really, the pressure times the area is force. Clearly, the force is proportional to the area. Now, let us put twice as many molecules in this tank so as to double the density, and let them have the same speed, that is the same temperature. Then, to a close approximation, the number of collisions will be doubled, and since each will be just as energetic as before, the pressure is proportional to the density. If we consider the true nature of the forces between the atoms, we would expect a slight decrease in the pressure because of the attraction between the atoms, and a slight increase because of the finite volume they occupy. Nevertheless, to an excellent approximation, if the density is low enough that there are not as many atoms, the pressure is directly proportional to the density. We can also see something else. If we increase the temperature without changing the density of the gas, that is, if we increase the speed of the atoms, what is going to happen to the pressure? Well, the atoms hit harder because they are moving faster, and in addition they hit more often, so the pressure increases. You see how simple the ideas of the atomic theory are. Let us consider another situation. Suppose that the piston moves inward so that the atoms are slowly compressed into a smaller space. What happens when an atom hits the moving piston? Evidently, it picks up speed from the collision. A special example: if an atom happens to be standing still and the piston hits it, it will certainly move. So the atoms are hotter when they come away from the piston than they were before they struck it. Therefore, all the atoms which are in the vessel will have picked up speed. This means that when we compress a gas slowly, the temperature of the gas increases. So, under a slow compression, a gas will increase in temperature, and under slow expansion, it will decrease in temperature. So, we now return to our drop of water and look into another direction. Suppose that we decrease the temperature of our drop of water. Suppose that the jiggling of the molecules of the atoms in the water is steadily decreasing. We know that there are forces of attraction between the atoms, so that after a while they will not be able to jiggle so well. So what will happen at very low temperatures is indicated in figure 1.4. The molecules lock into a new pattern, which is ice. This is a particular systematic diagram of ice, but is wrong because it is in two dimensions but right qualitatively. The interesting point is that the material has a definite place for every atom. The difference between solids and liquids is then that in a solid the atoms are arranged in some kind of an array called a crystalline array, and they do not have a random position at long distances. The position of the atoms on one side of the crystal is determined by that of the other atoms millions of atoms away on the other side of the crystal. Figure 1.4 is an inventor arrangement for ice. The one thing that you can see from the figure 1.4 is why ice shrinks when it melts. The particular crystal pattern of ice shown here has many holes in it, as does the true ice structure. When the organization breaks down on melting, these holes can be occupied by other molecules. So, whenever an ice melts, it shrinks. Now, although ice has a rigid crystalline form, its temperature can change. Ice has heat. If we wish, we can change the amount of heat. What is the heat in the case of ice? The atoms are not standing still, they are jiggling and vibrating. So, even though there is a definite order to the crystal, a definite structure, all of the atoms are vibrating in place. As we increase the temperature, they vibrate with greater and greater amplitude until they shake themselves out of place. We call this melting. As we decrease the temperature, the vibration decreases and decreases until at absolute zero there is a minimum amount of vibration that the atoms can have, but not zero. This minimum amount of motion that the atoms can have is not enough to melt a substance, with one exception: helium. Helium merely decreases the atomic motions as much as it can, but even at absolute zero, there is still enough motion to keep it from freezing. Helium, even at absolute zero, does not freeze unless the pressure is made so great as to make the atoms smash together. If we increase the pressure, we can make helium solidify.